This video is for section 10-11 about multiplying imaginary numbers. In the previous section, we learned that the symbol I does not represent a variable, but instead represents a particular number. And we also learned that when the letter I is by itself, that's called a pure imaginary number. Here is the definition for what I times I means. I times I is I squared. In turn, I squared is defined to equal -1. Here's another definition. If the letter A represents any real number and you multiply that to the imaginary unit, you write down the number right in front of the unit. For instance, if you want to figure out what 4 times I is, that's equal to 4i. Here's some examples. 2 times 5i, that's 10i. 7i times 6i makes 42i squared. But the I squared is equal to -1, and so the final answer is -42. We just discussed that I squared makes -1. Here's what happens when I is raised to other powers. I to the 0 power is equal 1, to fall in line with our definition of all numbers except 0 to the 0 power equals 1. I to the first power is just a single I. I times I makes -1. We had that definition earlier. I to the third power is equal to -I. Here's why that happens. Because I to the third power is I times I squared. Well, what's I squared? It's -1. And so I times -1 is -I. I to the fourth power is equal to +1. Well, why is that true? Because I to the fourth is I squared times I squared. Remember how I squared is -1? -1 times -1 makes +1. I to the fifth is equal to I. I to the sixth is -1. I to the seventh is -I. Notice this pattern, 1, I, -1, -I. We had that same pattern in this first column. So even though this chart doesn't continue farther, could you follow the pattern and get I to the 8th power? It's 1. What's I to the 9th? It's I. What's I to the 10th? It's -1. And what's I to the 11th? It's -I. And you could keep going on the chart. Here's the definition of additive inverses when you're working with imaginary numbers. Positive I and negative I are additive inverses because when you add them together, it equals 0. This definition is consistent with additive inverses of real numbers. Here is the definition of multiplicative inverses when you're working with the imaginary unit I. I and -I are reciprocals because I times -I equals -I squared, and that makes +1. Earlier this year when we were studying reciprocals, also called multiplicative inverses, we said that reciprocals are any two numbers that multiply together to make +1. So when working with the imaginary unit, it's I and -I that are reciprocals. That helps us to simplify expressions that contain the imaginary unit I. If we ever end up getting 1 over I, we can substitute -I in place of it. And if we ever end up getting 1 over -I, we can substitute I in place of it. Here's some examples. Simplify this fraction. Well, top and bottom both divide by 3, so this is 3 over 2i. This is equal to 3/2 times 1 over I. And we just discussed what you can replace 1 over I with. You can replace 1 over I with -I. So this answer is -3/2 I. If that's confusing to you, to replace an I in the denominator with -I, then the other way you could do this problem is to multiply the top and bottom of the fraction by -I. Then you get negative 3i over negative 2i squared. But what's I squared equal to? I squared is equal to negative 1. Negative 2 times negative 1 makes positive 2. And we get the same answer as we did here. Next example, we have 12 over I cubed. And we want to simplify this. From our table of powers earlier that involved I to the third is equivalent to negative I. We can replace a negative I in the denominator with the letter I. If that step's unclear to you, then here's how you can work it out step by step. Multiply top and bottom by I. This makes 12i over negative I squared. But what's the value of I squared? I squared is negative 1. And so we get 12i, the same answer. The definition I squared is equal to negative 1 means that the imaginary unit I is equal to the square root of negative 1. That's the reason why mathematicians use the symbol I, to represent the square root of negative 1. This theorem here allows us to simplify radicals that have negative numbers within a square root. I times the square root of r is equal to the square root of negative r. Until this point, whenever we had a square root of a negative number, we would say undefined or no solution. But over the set of complex numbers, we now can take the square root of a negative number. We're going to get the symbol I in our answer. Let's try an example of this. The square root of negative 16 plus the square root of negative 49. We could not do this problem until today. The square root of negative 16 is equal to the square root of 16 times negative 1. The square root of negative 49 is equal to the square root of 49 times negative 1. The square root of 16 makes 4, and the square root of negative 1 is the symbol I. The square root of 49 makes 7, and the square root of negative 1 is the symbol I. And then these are like terms, so the final answer is 11i. Next example. Let's simplify this one. So in the first radical, we can rewrite the negative 48 as 16 times 3 times negative 1. In the next radical, we can rewrite the negative 27 as 9 times 3 times negative 1. The square root of 16 makes 4, and that 4 gets multiplied to the 5 out front, making 20. The square root of negative 1 makes I, and the 3 stays in the radical. Over here, the square root of 9 makes 3, and that 3 gets times to the 1/3 out front, making a 1. The square root of negative 1 makes I, and this 3 stays in the radical. We have 20i square root of 3 minus 1i square root of 3. This is 19i square root of 3. If you want to, you can write the 19 square root of 3 in front and then put the letter I. If you do that, though, just be really careful you write the letter I after the end of the square root symbol. You don't want the I to look like it's under the radical bar. Next example. We have the square root of negative 8 times the square root of negative 2. The square root of negative 8 can be thought of as the square root of 4 times 2 times negative 1. And the square root of negative 2 can be thought of as the square root of 2 times negative 1. The square root of 4 is 2, and the square root of the negative 1 makes an I. And then this 2 here stays in the radical. Over on this piece, the square root of the negative 1 makes an I, and this 2 stays in the radical. Now let's multiply these together. 2i times I is 2i squared. And the square root of 2 times the square root of 2 makes a 2. In turn, this is 4i squared. But what's the value of I squared again? I squared is negative 1. So this answer is negative 4. In the last example, this is not simplified because of the radical in the denominator. Let's rewrite this as 14 over I times the square root of 7. Then rationalize the square root of 7 piece by multiplying top and bottom by the square root of 7. This makes 14 square root of 7 all over 7i. The 14 over 7 reduces to a 2 all over I. Problems are not simplified when there's an I in the denominator, so let's multiply top and bottom by negative I. Negative I is the conjugate of the letter I. This makes negative 2i times the square root of 7 all over negative I squared. But what's the value of I squared again? I squared is equal to negative 1. So the negative of negative 1 is just a positive 1. That's why multiplying by negative I fixes the denominator. So this final result is negative 2i square root of 7.